Hi everyone, welcome to the third video from chapter 17. So this video is really just to prep us for the interference and diffraction chapters, which come much later in the book. But this will really get us thinking about some topics in a more familiar environment than Young's double slit experiment, which is kind of tough conceptually for students to handle. Okay, so we're coming back to this idea that waves can interfere with each other, which we explored first in chapter 17 when we were talking about standing waves. So we were talking about superposition of waves. You can just add the displacements of two different waves, and they just pass through each other. So we're going to focus on this topic in more detail, but some interesting consequences. So really constructive versus destructive interference. So this problem right here gets at the heart of the issue. Two speakers, if they're connected and they're emitting sound in a very special way, so we have to focus on this word coherently and what this means. So these two sources are emitting sound coherently and in phase. And it turns out what that means is that there are certain points where these two waves will destructively interfere with each other. So there's a point. So this person is going to walk from infinitely far along this direction straight towards this speaker down here. And there will be a point where the sound waves cancel each other out and the person won't hear very much of anything. The reason we tend to not notice this in nature is that it really requires a advanced setup for this source to be emitting sound waves coherently with this. Like you really have to take care to set that up. Okay, so before we focus on that problem, I just want to focus on some of the assumptions that we're making and to give you a good picture of what's going on. So your book first talks about this in one dimension. So imagine I have a speaker here that's emitting sound waves like this. And then I'm going to have another source over here. I just learned how to draw a speaker a few minutes ago from the book, so my art skills are getting better and better. And this is going to be emitting sound waves similar to the other one. Okay, so already we're making some assumptions here. So I want to write these down. I'm going to focus more on this picture in a little bit, but let me focus on a few things here. Assumptions. So we have two different sources, but they're related in a lot of different ways. So one way that they're related is that the sources have the same, a lot of things. So they have the same wavelength. So notice how the waves that I'm drawing coming off of these speakers have the same wavelength. I intend to draw them with the same wavelength. They have the same amplitude. And the reason for that is that we're going to focus on constructive and destructive interference. So they have to have the same amplitude in order for them to be able to perfectly destructively interfere with one another. And then an additional assumption that I'm going to make that your book doesn't always make, but in this class I'm always going to make it, is that the phase difference is 0. So I guess I'll write this as initial phase. So in terms of my picture, what this means is that see how this wave being emitted right here at the same time as the wave being emitted right here, they're both at a maximum. So this is the relative phase between the sources. So we're not, when we talk about a phase difference later in this video, we're not going to talk about a phase difference upon the waves leaving the source. We're going to look at a phase difference from some observer. So we're going to have some observer here listening to the two sound waves. And there can be a phase difference because the phase of one of the waves would be different than the phase of the other wave by the time they get here. But at the time of the source, when these waves left the source, they were in phase. So when they have the same, when waves have the same wavelength and a specific wavelength, they're said to be coherent. And actually, I'm going to use the coherent to also mean I'm going to use the word coherent to also mean that they have the same initial phase. So unless you're explicitly told something about the phase difference initially, that they're out of phase by 180 degrees, when the sound is being emitted, then you can assume that they have the same phase to begin with. So your book has this factor delta phi naught, which is the difference between these two initial phases. So see how they have a phi 10, phi 20, and then taking the difference? That's the difference in the initial phases, and we're going to take that to be 0. So same initial phase, there's no phase difference there. Okay, so with those assumptions in mind, I want to keep this drawing going. And I happen to draw the wave. So for this picture in particular, the speakers are off by a certain distance that makes the sound waves destructively interfere. So obviously whether the waves are constructively or destructively interfere depends on this quantity right here. And this is called a path length difference. Okay, so delta x is called the path length difference. And it's describing how much farther did one wave have to travel as compared to the other wave. Okay, so whether an observer is here or whether the observer is here, it doesn't matter. The red wave traveled a distance delta x more than the blue wave. So the path length difference, no matter what point we're at along this line, as long as we're to the right of the blue source, the path length difference is the same. And it looks like for this picture right here, it looks like this delta x, it looks like it's one wavelength plus a half a wavelength. So it looks like this is 1.5 wavelengths for this particular picture. But in general, we just call that delta x. Okay, now, a lot of times we don't really care about the distance in meters. We just care about the phase difference. So there's a quantity that's a little bit more relevant when it comes to interference, and this is called the phase difference. So you can see that the red wave has undergone a full 2 pi radians, a full cycle, plus another half a cycle. So we can also describe this as the phase difference, and all we really care about is the magnitude of this. So this is going to be 3 pi radians. So there's a relationship between delta x and delta phi. Once you know one, you know the other one. So this relationship in general is that you can just take the path length difference, and then we want to say that for every lambda, so like if delta x was equal to lambda, delta phi would be 2 pi. If delta x were 2 lambda, then the phase difference would be 4 pi, etc. So this is how you can convert between path length difference and phase difference. So obviously it depends on the wavelength. So it depends on how far apart the sources are. I should be a little bit more general. This delta x isn't always the distance between the sources. It's how much farther. So it depends on the point of observation. So you find the distance. So you have some point where you're observing the wave, and you take the distance to one of the sources and the distance to the other source, and you subtract them. That's the path length difference. That's how much farther in distance one wave had to go as compared to the other one. And then you can quickly turn that into a phase difference. So the reason the phase difference is important is that we can see whether the waves constructively or destructively interfere with each other. So if delta phi, so more definitions here. So it looks like what I drew right here was destructive interference. You see how when we add, no matter if our observer was here or wherever along this line, it looks like these waves are exactly going to interfere destructively with each other. So in other words, when we add these two waves up, we're going to get 0 no matter what. So even if we wait a little bit, like if we wait a half a period, this wave is going to be a minimum, this wave is going to be a minimum. Remember the initial phase is the same. So all of these are going to flip 180 degrees, but it'll still be destructive interference. So this persists over time. Okay, so more definitions. So constructive interference. This happens when the phase difference is equal to, if it was equal to 0, plus or minus 2 pi, plus or minus 4 pi, etc. So any even integer multiple of pi, and you get that the waves would be on top of each other, and they would add constructively. So the sound would sound a lot louder than just from one of the sources. Alternatively, you can have, oh, and so by the way, so from this relationship between path difference and phase, or sorry, I said that vice versa. So this relationship between phase difference and path length difference, we can also say that constructive interference also occurs when delta x is 0, plus or minus 1 wavelength, plus or minus 2 wavelengths, etc. Okay. Destructive interference occurs when the phase difference is plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, etc. So an odd integer times pi in terms of phase difference, or delta x is equal to plus or minus a half a wavelength, plus or minus 3 halves wavelength, plus or minus 5 halves wavelength, etc. Right. Your book writes this in a way that I don't really like. So let me just write that delta phi is equal to, so it's equal to any number. You can separate out it's some number times 2 pi. Okay, and I don't like to have a separate formula for constructive or destructive interference. I just like to say that this equation is always true. And then if m is an integer, then we have constructive interference. And if m is a half integer, so by that I mean plus or minus 1 half, plus or minus 3 halves, plus or minus 5 halves, etc. If m is a half integer, then we have destructive interference. So your book instead has like 2 different formulas, and what they mean by m is different. I think it gets really confusing that way. I like to just have one equation and then solve for the value m. That's saying how many cycles they're off from each other. So if they're off by a perfect number of cycles, then they're constructively interfering. If they're off by a perfect number of half cycles, then they destructively interfere perfectly. Okay. Okay, so your book separates this into 2 sections. They have 1D problems where all the waves are going along the same line. They go into the math a little bit, but really we're going to get into we're going to look at other applications of this with light in later chapters. I'm going to hold off on that, and then examples in 2 or 3 dimensions. So it's really the same equation. It's just instead of delta x, they plugged in delta r. So you just have to take into account that, you know, there's 2 different distances. So there's 1 point of observation, and there's 2 different sources. So you get the 2 different distances, and then you subtract those 2 different distances, and that's your delta r. And there's the same relationship between path length difference and phase difference. And again, we're going to take the delta phi naught to be 0. We're just going to say that the sources start out in phase. And that's about it. That takes us to the end of the section. So we just have to solve this problem here. Okay, 2 speakers emit sound coherently. So I'm going to, so the way to think about these problems is that you want to, and I guess they have a table here. The way I would suggest always to think about these problems is to take your point of observation, so that's wherever the person is right here, and find what the path length difference is. So a lot of times you can just use the picture to find out the path length difference. So I would say that, so here I just need the distance right here. So what's the distance from the observer to the speaker over here? And then minus d is going to be the distance from the observer to this closer speaker. And that'll give us the path length difference right away. And then we can turn that into a phase difference. All right, so let's do that. So the original problem. Okay, so the path length difference, so delta x or delta r, I mean your book all of a sudden switches to delta r, but they mean the same thing by it. Delta r is going to be So the distance to the first speaker is, by the Pythagorean theorem, d squared plus 3 meters squared. So I'm going to be a little sloppy here and not write the meters, and just know that we're working in meters. So we have that minus d. Okay, notice how that's a positive number. All we really care about is the magnitude, because remember, it's whether it's positive or negative that we will know that it's constructive or destructive interference. So by the way, notice how if d is infinitely big, as d grows without bounds, so this person's coming from infinitely far away. As d gets infinitely big, you can show, if you're good with limits and you know that part of calculus, you can show that delta r shrinks down to 0. So one way to convince yourself of this is just play with a calculator. Plug in 100 for d or 1,000 for d, take that difference, and you can see you can get that difference as small as you want. So we start off so that when the person's infinitely far away, it's actually constructive interference. I mean, the sound isn't super loud because you're infinitely far away, so it's not too useful to say that it's a point of constructive interference. But the point is that as d decreases, so one mathematical note to note for this problem in particular, as d decreases, delta r increases. That's just for this problem, right? It depends on the geometry of the problem. So in particular, you go from 0, so delta r starts out at 0 when d is infinitely big, and will go up. So the problem asks, at what distance will, and we're going to call that special value of d star, at what special distance will this person hear destructive interference for the first time? So delta r is growing from 0 to some value, and that value when the person hears destructive interference for the first time is when delta r is 1/2 times the wavelength. Okay, so the first point of destructive interference, so the first time we have deconstructive interference, we have destructive, not deconstructive. We have destructive interference is when delta r is equal to 1/2 of a wavelength. Now we could convert to a phase difference and say that it's pi, but there's no reason to. So you just need to be able to go back and forth quickly between phase difference and path length difference. And which one you're using depends on which problem you're solving. Here we know the geometry, so it makes more sense to work with delta r's. And we know we were actually given in the problem what lambda is. So it makes a lot of sense to just deal with lambda right away. Okay, so we're going to require that delta r is 1/2 lambda. So if you ever see this, an equal sign with an exclamation mark above it, it means we require this to be true. So we're going to demand this and see what we get out of it. So d star, so I'm going to now, so this equation was true for any d, you get a path length difference. For this special path length difference, I'm going to call that special value of d star. Okay, so we have this. So now it's just solving for d star. So that square root is the ugliest thing in here, other than the exclamation mark. So I'm going to add d star to both sides and square both sides. So we have 1/2 lambda plus d star squared is equal to d star squared plus 3 squared. So then I'm going to expand out the thing on the left. And this is looking good because the d star squared will cancel out from both sides. So this is not going to be a quadratic form equation. It's just going to be a linear one. So this will be nice. So this is 1/4 lambda squared plus lambda d star, and then plus d star squared, but that's going to cancel with this d star squared. So this just leaves equals 3 squared. So we're almost done. D star is 9 minus 1/4 lambda squared over lambda. And if we plug in here, lambda was 2 meters. That was in the original problem statement. So 2 squared is 4. So 9 minus 1 is 8. Divided by 2 is 4 meters. So it looks like when that person gets to a distance of 4 meters from the speaker on the bottom, that's not a coincidence. Actually, when I designed this problem, I had in mind a 3, 4, 5 triangle. So 3, 4, it looks like the distance to this speaker is 5 meters. So the path length difference here is 1 meter. So 5 meters and 4 meters, the path length difference here is 1 meter, which is exactly half of a wavelength. So that's perfectly destructive interference. So if we were in class, we could do a demo where I set up the speakers and you can actually walk and hear hear where that destructive interference is, but unfortunately we don't have that available. So you can try and do destructive sound waves, destructive interference with sound waves. Try typing that on YouTube and see what you get out of it. You might be surprised. Okay, so we're going to continue constructive and destructive interference with light in chapter, I think it's 33, but in the next video.